Okay, so today we're going to start a new topic which is going to be very important for the next half of the course when we start to develop the statistical mechanics, and this topic is entropy. So I will start just by defining what we mean by entropy, and then I'll go on to explain why it's so important. Okay, so let me define it. We define the change in entropy of a system. Entropy is given the symbol S, capital S, as the integral from over time, so from time t1 to time t2, say, of the 1 over the temperature of the system times the rate at which heat is going into the system, integrated over time. This is 1 divided by the temperature. This is the rate at which heat goes in. And then if you integrate that over time, this is the definition of the change in entropy. So you can write this in an approximate form like this. Is the integral from the original to the final state of the system of dq over t. Here 1 denotes the initial state, 2 denotes the final state. Okay. So that's how it's defined. Let me just give you a very simple example to illustrate this. Calculate the change in entropy for an isothermal expansion of the ideal gas. Okay. So to do this, we say, well, it's isothermal. This means that the change in temperature is 0, which means that the change in internal energy is 0. And then the first law of thermodynamics, therefore, tells you that the change in heat must be equal to the change in work. And we already know that if a small amount of work is equal to pressure times the change in volume. So therefore, the change in entropy is equal to the integral from the initial state to the final state, dq over t. That's the definition. Then I can use this result for dq to say that this is the integral from v1 to v2 of p over t dv. Now I can use the fact that it's an ideal gas, so in other words, pressure times volume is equal to number of particles times Boltzmann constant times temperature. So P over T is equal to nk over V. This is the integral V1 to V2, n Boltzmann constant over V dV. So these are constants. So I've got an integral of 1 over volume d volume, and this gives me a log. So the final result is that the change in entropy is equal to number of particles times Boltzmann constant times the log of the volume, ratio of volumes. Okay, so this is an example of how you can calculate it based upon the definition. For an isothermal expansion of an ideal gas, you get this result. So now I've defined it, it's a bit of a strange definition, I want to explain why it's so important. And to explain why it's important, I'm going to give you two results about it. The first one is that entropy is what's known as a state property. What this means is that the change in entropy between any two states of a system is independent of the path you take between those two states. So the change in entropy between any two states, 1 and 2, is independent of the path taken. That's what it means to be a state property. So I can illustrate this on a pressure volume diagram as follows. Suppose I start in some state up here, let's call this one state 1, and I end up in some state down here, let's call this one state 2. There are many different ways of going between these two states, right? I could do a kind of smooth expansion like this, or I could go down and then across. Or, I could do something, really crazy if I wanted to. There are lots of different ways of going between these two states. Lots of different ways to change the system. What it means that entropy is a state property is when you calculate the change in entropy of all of these different paths, you find that they have the same change in entropy. So when you calculate the change in entropy along any of these paths, it's always the same. This fact is not clear from its definition, but is found empirically. When you do experiments, you find that this is true, okay? Even though it is not immediately clear from the definition of entropy. So that's a state property. It means that if I go between two states of a system, the path I take doesn't matter. So many other things are also state properties. Change in entropy is a state property. The temperature is a state property. Right? Temperature here and here doesn't depend upon the path you take. The volume, pressure, internal energy U, all of these things are state properties. Which means I only need to know the point to define these properties. I don't care about the path taken to reach that point. The second point about entropy, which makes it a very important property, is that it can be used to express a physical law known as the second law of thermodynamics. So I will explain what this is. It says that for a closed system, the total entropy always increases with time. Okay, so can write this down as an equation quite simply. If I take the change in entropy with respect to time, then this is always greater than or equal to 0. Right, so this law is very important, and probably in the next lecture we're going to talk about some of its effects. So for now I just want to note some things about this. First of all, closed is a technical term here. A closed system means that you don't allow any external influences to affect the system. So in particular, no energy or momentum or whatever is transferred to the system from outside. Okay, so it's closed in the sense that nothing outside influences the system. The system's dynamics are only determined by the internal dynamics of the system. Okay, that's what it means to be closed. I'll give you some more terminology now. You see that the second law says that the change in entropy is greater than or equal to 0. Now, if the change in entropy is equal to 0 along some process when you change the system, then the process is called reversible. And if the opposite is true, ds by dt is strictly greater than 0, then the process is called irreversible. So that serves as a definition of these two terms, reversible process and irreversible process. Okay. So I want to give you an idea of why these terms make sense. Reversible means you can do the opposite of something, right? So suppose I started with my system in some state 1 here, and I ended up in some state 2 here, and I went along this way in a reversible process. So in other words, ds by dt is equal to 0 as I go along this way. And suppose I can also get the same change of state, why not, from a different kind of system, a different kind of process, sorry. And as I go along this process, there is a strictly positive change in entropy. Now suppose I try to go back. Okay, so I've gone from state 1 to state 2. What happens if I try to go back to state 1? Well, if I'd gone through an irreversible process from state 1 to state 2, then the change in entropy is positive. In order to go back, I would have to have a negative change in entropy. Right? If the change in entropy is positive this way, then going back it will be negative. But the second law says it's not possible. It's not possible to get a negative change in entropy. So for this process, I can go this way, but I cannot go the other way. It's not allowed. Okay? The second law of thermodynamics says you can't go back. But if the change in entropy is 0, then I can go both ways. I can go this way and I can go back. Because in both cases, change in entropy is 0, and that satisfies the second law of thermodynamics. So processes are called irreversible, that's this blue one here, because you can't undo them. You can go this way, but you can't go back. Reversible process, you can do both ways. Okay, and one final note. So if I've got this closed system, this closed system can undergo some changes. Each time it undergoes a change, the entropy must increase. That's what the second law says. When the state of the system changes in time, the entropy must increase. So if you wait long enough, you may reach a state which has maximum entropy. Once you reach the state of maximum entropy, you can't increase anymore, by definition. So the state of maximum entropy is necessarily an equilibrium. Once you reach this state, you can't change, because the second law says you can only increase entropy. Once you reach the maximum entropy, you must stay there. So the state of maximum entropy is an equilibrium. It's a stable state. Once you reach the state of maximum entropy, you can't leave that state unless there is an external influence on your system. Okay, so I've defined what entropy is, and I've defined why it's important. Firstly, it's a state property, the path doesn't matter. And secondly, the second law of thermodynamics says that the entropy must always increase. So now I just want to look at a series of examples to try and develop this concept of entropy some more. So for the rest of this class, I'm going to look at various examples of these processes. Okay, before I do that, let me say that this fact that certain processes are irreversible because of the entropy requirement is very important for the world as we see it, right? A classical example is if I take a glass filled with water and I drop it and the glass smashes, that results in an increase in entropy. Okay? So before there was a glass here in one piece, as I drop it and it smashes, the entropy increases. That means it's impossible to go back. It's impossible for the little bits of glass to reassemble and to form a perfect glass in my hand. So the fact that entropy is always increasing is why you see glasses smash, but you never see them come back together again. It's driven by the second law of thermodynamics. Right, okay. Right, so now let me develop some examples. So, first of all, I want to consider just a very simple example where I have two systems which are joined together. The first system is at temperature T1, the second system is at temperature T2, and they are joined together and then they are closed from the environment, so they are thermally isolated from everything else. Now, as a result of the temperature differences between these two systems, it's possible that heat can flow from one to the other, right? For example, if this one is hot and this one is cold, you would expect heat to flow from the cold one to the hot one. Right, so let's work out what does the change in entropy look like in this case. Well, the change, let me do a small change, a small bit of heat transfer. The change in entropy of the first system is equal to the amount of heat going in, well that's delta Q, divided by the temperature of the first system. That's the definition. The change in entropy of the second system is equal to the energy going in, well as I've drawn it, that's minus delta Q, because as I've drawn it, Q is going out rather than in, divided by the temperature of the second system, that's T2. So we get a total change in entropy which is the sum of these two. Delta S is equal to delta Q, 1 over T1 minus 1 over T2. Okay. So if I imagine this process changing over time, then the rate of change of entropy with respect to time is equal to the rate of transfer of heat times this difference of the inverse temperatures of the two systems. And we know from the second law of thermodynamics that the change in entropy must always be positive, so we must have that dq by dt times 1 over T1 minus 1 over T2 must be greater than 0, because the change in entropy must be greater than 0. Now let's look what this means. Well, first of all, if temperature 2 is bigger than temperature 1, so if T2 is hot and T1 is cold, in this case, 1 over T1 is bigger than 1 over T2. So in this case, this is positive. So in this case, this is also positive. So that means if T2 is bigger than T1, then heat will flow from system 2 to system 1. So if this one is hot and this one is cold, then heat flows from the hot to the cold. In the other case, if this one is hot and this one is cold, so T1 is bigger than T2, then this thing is negative. Right? If T1 is bigger than T2, then this is negative. That means dq by dt must also be negative. That means that heat must flow from T1 to T2. So in both cases, if this is hot and this is cold, then heat flows this way. If this is hot and this is cold, then heat flows that way. So the second law of thermodynamics implies that the heat will flow from the hot system to the cold system, which, as we all know, that's what it does. So let me write that now. So if T1 is greater than T2, no, let me do the other way around first. If T1 is less than T2, then 1 over T1 minus 1 over T2 is greater than 0, which implies that dq by dt is greater than 0, which means that heat flows from 1 to 2. Sorry, heat flows from the other way around, right, as I've drawn it. Heat flows from 2 to 1. And in the opposite case, the reverse is true. So if T1 is greater than T2, then this thing is less than 0, which tells me that the rate of heat flow is less than 0, as I've drawn it there. That means that heat is flowing from 1 to 2. So this tells you one very important consequence of the second law of thermodynamics. Heat always flows from hot to cold. The second law implies that heat always flows from the hot system to the cold system in a closed system, right? It's important to specify in a closed system. Air conditioning is an example. An air conditioner moves heat from cold to hot. Okay, so that does the reverse, but with an air conditioner, energy is coming from outside. Right? You have to put in electrical energy to shift the heat. In a closed system, the heat will always go from the hot body to the cold body. Okay, another thing we can say is if I draw a graph of the total entropy as a function of the temperature T1, then and let's suppose that T2 is somewhere here, if T1 is greater than T2, then decreasing T1 gives an increase in entropy. If T1 is less than T2, then decreasing T1 gives you a drop in entropy. Okay? So at the equilibrium point, when the two temperatures are equal, the entropy is maximized. And this is what I stated. Well, it's an example of the result I stated. The state of maximum entropy is an equilibrium state. In this case, maximum entropy occurs at thermal equilibrium when the temperatures are equal. Okay, so this is an important result. You get maximum entropy when the temperatures of the two systems are equal. So this is the second example. And I do this example just to check that entropy is a state property, as I told you it was. This example is in order to check the fact that entropy is a state property. Okay. Now, we've already calculated change of entropy in one case in a PV diagram, and this is the case for isothermal expansion of an ideal gas. We said if you start here and you go down here, so this is isothermal. So I started at temperature T, I end at temperature T. Then, if the change in volume is V1, V2, we calculated that the change in entropy was equal to number of particles times the Boltzmann constant times the log of the ratio of volumes. We got this result. Now, I claimed that entropy is a state property. That means however we move from this point to this point, we should get the same number. So I just want to check that's the case for another simple example. And I'm going to take the case where instead of doing an isothermal expansion, I first do a process at constant volume like this, and then I do a process at constant pressure. So let's call these pressures as well, P1, P2. Okay, so instead of calculating entropy along the isothermal expansion, I'm going to calculate it along this direction, and provided that entropy is a state property, as I said, we should get the same answer, right? Which is that. So first of all, we do process at constant volume, then process at constant pressure. Let me call this, because I'm using this notation for the problems, let me call this A and B. Okay. So first of all, what's going on along A? Well, A is a process at constant volume, which implies that the change in heat is equal to the number of particles times heat capacity at constant volume times the change in temperature. It's the definition of heat capacity. Right? So therefore, the change in entropy, delta S A, let's call it, is equal to the integral dq over T. And I substitute this for dq, so this is equal to NCV integral dt over T. And this integral goes from the initial temperature, which I just called T, to the final temperature here. Let's call this temperature T prime. Okay. So between T and T prime. And again, this is a log, so this turns out to be N times the heat capacity times the log of T over T prime. That's the entropy change along process A, and we can do the same analysis along process B. Okay, so the change in entropy along process B. Okay, but B is at constant pressure. So in this case, we have to use the heat capacity at constant pressure. So change in heat into the system. So heat into the system is equal to the number of particles times the heat capacity times the change in temperature. So therefore, the change in entropy is equal to the integral dq over t, which is, now substitute this, n times the heat capacity times the integral dt over t. And now we're going from the reverse, so we're going from temperature T prime to T. And this gives you NCP times the log of T over T prime. Sorry, in which case this one is wrong. Sorry. Here, T prime is up here, right? T prime over T. This one's T over T prime. Okay, so the total change in entropy is the sum of these two. So I'll just write it. First of all, NCV log T prime over T plus NCP log T over T prime. Now we can simplify this a bit. Log of A is equal to minus log of 1 over A. Right? So I can write this as N times Cp minus Cv times the log T over T prime. And I know for an ideal gas that the difference between the two heat capacities is just equal to the Boltzmann constant. So because this is an ideal gas, I can write this as N times the Boltzmann constant times the log T over T prime. And what I want to show is that it's the same as this, right? I want to show that the change in entropy does not depend upon the path. So this should be equal to this. Right? These two things should be equal. You can see that the form is nearly equal. NKB is the same. I've just got to show that V2 over V1 is equal to T over T prime. Now I can do that by just using the ideal gas equation of state. We have that if I look on this graph, at this point here, I'm at pressure P2, volume V1, and here I'm at pressure P2, volume V2. Right, so the ideal gas equations of state tell me that P2 times the volume, which is V1, is equal to N times the Boltzmann constant times the temperature there, which is T prime. And at the final point, the pressure is P2, the volume is V2, and this is equal to N times Kb times the temperature T. And you see that if I divide these two equations together, I get the result. Okay, if I take this divided by that, then I get that V1 over V2 is equal to T prime over T. And therefore, delta S, which is N Kb log T over T prime, is equal to N Kb log V1 over V2 over V1, okay, which is the same as for the isothermal. Okay, so that's the end of this example. What we've done is we've taken two states of the system and considered two different ways of going between them, one as an isothermal expansion and one as a constant volume plus a constant pressure process. We've calculated the entropy, and we've shown that the change in entropy is the same in both cases. So as I said, entropy is a state property. It doesn't depend upon the path. Okay. Now we move on to our third example, and this is an example of free expansion, which is a kind of expansion that we haven't considered yet, but let me explain what it is. Suppose I've got gas in an isolated system, like this. But I put some kind of barrier in this system. Draw it in blue. I put some kind of barrier into this system which holds all of the gas on one side of the box. So I start off like this, and suppose I'm at temperature P1, volume V1, sorry, pressure P1, volume V1, temperature T1. Okay, now I start like this, and for a free expansion, at some point I suddenly remove the barrier. So the gas is contained, and at some point I suddenly, in a negligible amount of time, remove this barrier, and therefore the gas will expand to fill the space. So this is a very rapid expansion. And suddenly remove barrier. Okay. And after I remove the barrier, we then go into the state where if you wait long enough, you go into the state where the gas has filled now the whole box. Okay, and it's at pressure P2, volume V2, temperature T2. So I want to say, how does this initial state relate to the final state? Well, if we suppose that this is an ideal gas, then, well, it's thermally isolated, right? It's thermally isolated so that no heat has gone into the system through this process. Also, I do no work in removing the barrier. Okay? The gas does no work because the gas is pushing this way, but I'm removing the barrier at 90 degrees to it, to the force of the gas. So no work is done by the gas or done to the gas. So work done is also zero. Okay? And this means that in a free expansion, the change in the internal energy of the gas is equal to zero. So in a free expansion, there is no change in the internal energy of the gas because you don't heat it, you don't do any work to it, or it doesn't do any work. Okay. Now for an ideal gas, we know that the change in internal energy is just number of particles times the constant volume heat capacity times the change in temperature. So if there's no change in energy, there must be no change in temperature. So therefore, delta T is equal to 0. In other words, T1 equals T2 equals some temperature T. That means that as long as this gas is ideal, the initial and final states are the same as if this gas had expanded isothermally. It started out in a state at temperature T, it ends up in a different state at the same temperature. So the initial and final states are the same as for an isothermal expansion. the initial and final states. Are the same as for the isothermal expansion. Which we calculated already. Delta S is n kb log the ratio of volumes. Now in this case it expands, so V2 is greater than V1. So this is greater than 0, strictly greater than 0, and therefore the process is an irreversible process. Change in entropy is greater than 0, so the process is an irreversible one. When you think about it, it makes sense that this process should be irreversible, because what have we done? Well, we started off with the gas in one half of the box. We remove the barrier, and the gas fills the whole box. Okay? The gas left to its own devices will never go back into the original half of the box. So while you can allow the gas to expand, the gas will never choose to be compressed to half the size of the box again. If I want to go from this state to this state, I have to physically do work to compress the gas. In other words, this is an irreversible process. You can go this way in a closed system, but you can never go that way. Okay, I want to finish this example with a final note. In the other kinds of expansions I've talked about adiabatic expansions, isothermal expansions, and so on. We always drew them on a PV diagram. So, for example, this is the isothermal expansion here, temperature T. Temperature T. So you might ask, well, what does the line of a free expansion look like? Okay? If I do a free expansion and I try and draw it on here, what does it look like? Well, the free expansion is a type of expansion which you can't draw on a diagram like this. So it's not possible to draw the free expansion path on a pressure volume diagram. The reason is, as this gas expands, the pressure and the temperature is not a constant throughout the gas. This is true because pressure and temperature are not constant throughout the gas. Throughout gas. Okay, I want to do one final example before we finish, and this is an example of a reversible process, so one where it is possible to go both ways. This is called a quasi-static. I'll explain all these terms later, by the way. Quasi-static isothermal expansion of the ideal gas with a reservoir. So let me draw a picture to say what I mean. It's similar to pictures I've drawn before. I have the gas in a box, thermally isolated box. I allow the volume of the gas to change through a piston which is also thermally isolated and has a constant force applied to it, which controls the pressure of the gas. And I control the temperature of the gas by putting a reservoir which has a fixed temperature T. Okay? So I've got the gas here, the reservoir which controls the temperature of the gas, and the piston which controls the pressure of the gas. Okay. So as it expands, heat will go from the reservoir into the gas. Okay, so this is what we do. We slowly is a very important word here. We slowly reduce the force F on the piston so that the gas and reservoir are always at the same temperature T. Okay, so this is a closed system if I consider it consisting of a reservoir and a gas. And if we do it slowly, we can assume that roughly the reservoir and the gas remained at the same temperature T. And in this case, we will see that the process is reversible. It's possible to go both ways. So first of all, what's the change in entropy of a gas? Well, this is an isothermal expansion, which we've seen many times before. Okay, let me write down the definition. Integral dq over T, which is NK B log V1, V2 over V1. So this is just the isothermal result we've seen before. Now if I look at what's the change in entropy of the reservoir, RES always stands for reservoir, then this looks very similar, except the heat going into the reservoir is minus the heat going into the gas. If I call Q the heat going from the reservoir to the gas, then the heat going from the gas to the reservoir is minus Q, right? So this is exactly the same integral as that, except with a minus sign. So the result is exactly minus NKB log V2 over V1. So in an isothermal expansion, a slow isothermal expansion with a reservoir, the change in entropy of the gas is minus the change in entropy of the reservoir, and therefore the total change in entropy is 0. Total change in entropy, which is equal to the change in entropy of the gas plus the change in entropy of the reservoir. This is equal to 0. And because the total change in entropy is equal to 0, this means that you can go both ways. So this is an example of a reversible process. Okay, so this is our first example of a reversible process, and we did it by assuming that the gas is in contact with this reservoir, and we change the state slowly. It's very important that we change the state of the gas slowly. If we change it quickly, that means we allow the gas to expand quickly, then the temperature of the gas will drop. If the temperature of the gas drops, then the temperature of the gas is lower than the temperature of the reservoir. And in this case, we've seen that the process is irreversible. Okay. So if you want it to be reversible, you have to do it so slowly so that the two systems always remain at the same temperature. If you do it fast, they create a temperature difference, and this means that you get a positive increase in entropy, which you can't undo. Okay, so this defines basically what our quasi-static process is. If you want to do a process in such a way that it's reversible, you have to do it infinitely slowly, so that the components of the system are always in perfect equilibrium with each other. This defines what's known as a quasi-static process. So the state of the system changes very slowly, so slowly, that the components are always in thermal equilibrium. And it's only these kind of processes which can be reversible. Only these very slow processes can be reversible. So if you want to make a process where there's no change in entropy, you have to do the whole thing very, very slowly. You have to move the piston in the gas very slowly, for example. Okay, now in reality, there are no processes like this. Okay? In the Stirling engine I showed you last time, the piston goes up and down fast. Okay? In a car engine, the piston goes up and down fast. So in practice, there are no reversible processes. In the real world, everything is irreversible. In reality, there are no reversible processes. So this idea of a reversible process is a theoretical one. We can theoretically make reversible processes where we do it very, very, very slowly. But in reality, there is always some increase in entropy. No matter what you do, there is always some increase in entropy. So all thermal processes which occur in nature are irreversible. They can only go one way. And this is really the state of the world as we know it, right? Every action you do has some effects which are irreversible. If I just walk as I've been walking and talking, some of my energy is dissipated as friction when my foot hits the floor. This friction generates heat. This heat increases entropy. So just as I walk, I am doing an irreversible process. I'm increasing entropy. As I talk, the sound is energy coming out of my mouth, right? This energy is also dissipated as heat. It sets up vibrations in the air. This warms up the air. So my speaking is also irreversible. I am sending out sound energy, which is turning into heat. This is an irreversible process. It's impossible to undo. So in reality, all of the processes which we undertake every day are irreversible. They can only go one way. Note on the second law. The first point I wanted to make, which I don't think I made last time, the second law tells you that entropy is always increasing with time. This means it makes a distinction between time going forwards and time going backwards. If you're going forwards in time, the entropy is increasing. If you're going backwards in time, the entropy is decreasing. So this is called time reversal asymmetry. The physics looks different depending whether you're going forward in time or backwards in time, right? And it's the only source of time reversal asymmetry in classical physics. If you look at electromagnetism or you look at, say, Newton's laws, they all have time reversal symmetry. That means Newton's laws look exactly the same as whether time is going forwards or backwards. There's no distinction between the future or the past. But the second law does make a distinction between the future and the past, because it says if you're going forwards in time, entropy is increasing. So the second law is the only source of time reversal asymmetry in classical physics. Now, when you go to quantum field theory, there are other sources of asymmetry, but these are not particularly relevant to the microscopic world in which we live. Okay? So this time reversal asymmetry means that the past is different from the future. Distinction of past and future. And this is a very important thing to note, because from our perspective as human beings, the past and the future are completely different, right? We have a memory of the past. We know what happened in the past, but we don't know what will happen in the future. We know that certain processes, like I talked last time about dropping a glass, only work in one direction. If you drop a glass and it smashes, it will never reform into a glass of its own accord. So all of these are examples of the time reversal asymmetry, the distinction of past and future, but physically, the only source of this asymmetry is the second law of thermodynamics, is the behavior of entropy. And the second point I wanted to make is I stated the second law of thermodynamics is saying entropy is always increasing, but you can state it in various other ways which are equivalent. The equivalent statements of the second law. So the first one is the one that I stated. So it says that ds by dt is always greater than or equal to 0 in a closed system. So if your system is closed, the entropy must always increase. That's the way I stated the second law in this course. The second statement is known as the Clausius statement. Clausius was a scientist in the 19th century. And he said this is equivalent to saying, if I have two bodies, one which is hotter and one which is colder, then the heat will always go from the hotter body to the colder body. So it is impossible for heat to flow from a cold body to a hot body without doing some work on the system. So we talked about systems which do transfer heat from a cold body to a hot body. For example, a refrigerator does exactly this. But what the second law of thermodynamics says is you have to do work. So when you use a refrigerator, you have to use electrical energy. And this statement is saying that it's impossible to build a refrigerator which does not require energy. Heat will only naturally, of its own accord, flow from hot to cold. That's the statement. Okay, there are two more statements I want to say before I finish. The next one I will call the Carnot statement because it refers to Carnot cycles, not because it was stated by Carnot. The Carnot cycle is most efficient And the efficiency of the Carnot cycle is given by 1 minus the ratio in temperatures. And finally, this is what's known as the Kelvin statement, which is also equivalent. This says that you can't get work out of heat alone. So if I have a very hot system, I can't get the energy in a useful form out of that system without putting it in contact with a colder system. So it is impossible to extract work from a system. No, sorry. I need to be more precise. It is impossible to extract work in a cyclical fashion from an isolated system at temperature T without connecting it to a system at lower temperature. So I made this point in the very opening lecture when I showed you the working of the Stirling engine. The Stirling engine works because there's a difference in temperatures. Okay? If the temperature is the same throughout the Stirling engine, then it's impossible. It doesn't work. There's no way you can get useful energy out of the system. Now, this applies no matter how hot the system is. So if I take a system and I heat it up to 100 degrees or 1,000 degrees or 1,000,000 degrees, if there's no temperature difference within that system, you cannot get work out of it. Even though at 1,000,000 degrees there's a lot of energy there, you can't extract it. You can only extract it by putting it in connection with the system at lower temperature. So as an example of this, when I was at university, one of my friends, he was from Thailand, and you know Thailand is very hot. So he was asking me, thinking in terms of natural resources, the thing that they have in Thailand is lots of heat. It's a very hot country. So he asked me, is there any way that we can use this heat to generate energy? Right? We've got a lot of heat. Can we use it to generate energy? And unfortunately, the answer is no, because of this. Okay? If you have a hot system, you can't get useful energy out of it unless you connect it to a cold system. So heat alone does not allow you to extract energy.